Alright guys, here we go. So we are going to do first problem of the unit. So this is collision analysis, and this is momentum and collision. So we're going to do number 1. Alright, here we go. Easy money. So let's read it, then let's highlight, because highlighting is awesome. We'll look at a couple of formulas, and then we'll just get rocking and rolling. First column's easy. Second column, we got to think a little bit, and the third column's pretty easy too. We will have to think just a little bit though. So, a 10 kilogram medicine ball is thrown at a velocity of 15 kilometers an hour to a 50 kilogram skater who is at rest. Skater catches the ball and subsequently slides across the ice. I don't really care about that. Consider the skater and the ball as two separate parts of an isolated system. No external forces. That's important. And then fill in blah, 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 blah. Cool. So let's highlight what we probably need. So here's a mass. 10 kilogram medicine ball. That's important. And the velocity of the medicine ball. Here's the mass of the skater. And the velocity of the skater, notice it says rest, so that means 0. Anytime it says it's at rest, velocity equals 0. Okay, notes time. I'm going to start taking them right here. So, a couple things we need to know. We need to know that the initial velocity is p, always equals in a closed system, which it says here, isolated system, the final velocity, f, right? So initial always equals final in velocity. We also need to know that velocity equals momentum equals mass. Did I call this velocity? My bad. Let me repeat all this just so it's clear. Initial momentum is p equals momentum equals final momentum. Momentum equals mass times velocity. Okay, we're clear. We fixed that. We repaired it. We're good. So, now let's look at another formula. Because we know initial momentum equals final momentum, we have two objects. We have the medicine ball, and we have the skater. There's our skate, right? So we know that the momentum of the medicine ball plus the momentum of the skater, this is initial velocity. Remember, this stands for mass, because momentum is mass times velocity. So the momentum of the medicine ball plus the momentum of the skater, initial, equals the final momentum of the medicine ball plus the final momentum of the skater. So this is the skater in the end. This is the medicine ball in the end. This is after collision. This is before collision, right? So with that being said, let's plug in what we know. So the medicine ball, the mass is 10 kilograms. So 10, parentheses, the velocity is 15 kilometers a second. 15 kilometers per hour. Sorry. It says hour, Mr. Bears. What are you doing? What are you doing? Alright. Plus, now we're doing this. We got to kind of slightly shift, so just assume it's all kind of shifted like that. The skater's mass is 50 kilograms times the skater's velocity. Well, it doesn't say a number, but it does say they started at rest. So at rest means 0, right? So times 0. So we already know what this is going to be. Equals, again, mass is the same. Doesn't matter before or after, mass is the same. So 10 kilograms. We don't know final velocity, so let's just put final velocity plus mass is 50 kilograms. And then times the final velocity. So let's combine this stuff. So this times this is 0. This times this is 150 equals, we still don't know. We know it's 10 kilograms times final velocity plus 50 kilograms times the final velocity. So we have something to plug in. So let's go back to this. Remember, mass times velocity is what? Momentum, right? Which means the momentum of the medicine ball in the beginning was 150. So we can put that here. Momentum of medicine ball, 150. 50, right? The momentum of the skater in the beginning, well, it's 50 times 0, 0. Bam. So the total momentum, we just combine these. So that's pretty easy, right? So this one is going to be 150. So that's how we got this first column. This column was easy, right? Momentum after, that's the right side, right? So everything on this side, this is like the after, right? Is, we don't know yet because we have the mass, but we don't have this final velocity. But we're going to figure it out. So we have right now 150, let me see that? Let's move it up. 150 equals 10, I'm going to put this back in later, times final velocity plus 50 times final velocity. We remember from algebra, if both of these are this times final velocity and this times final velocity, we can take this out. So we can do 150 equals parentheses 10 plus 50, mass plus mass, times this final velocity that we just took out. Because we know we could just redistribute that algebra style, right? So we're good to go. With that being said, let's combine these. So this is 60, right? So it's 60 times the final velocity equals 150. Okay, so we got to algebra this. When I see this attached by multiply, I got to divide it out. So we cancel that. So that means we got to do the same side to the other, same thing to the other side. So 50 divided by 60, it goes in once, twice is 120 plus a 0.5. So it final velocity, let's do the old flipperoo, equals 2.5. So that we just found out the final velocity. So is there a final velocity on here in these ones? No, but it does ask us here. So you can show all your work and eventually you're going to put the final velocity equals 2.5. Now, remember, we got to find the momentum after. Well, again, we know that momentum is mass times velocity, and in this case we want the after, right? So that means the right side. So if we do mass times velocity, we know the mass. So the mass of the medicine ball was 10. And our final velocity, well, we already said that. Oh, there we go. 2.5. So let's just figure it out. So 10 times 2.5, that's our final momentum of the medicine ball. So if it's multiplied by 10, we just move the decimal ones to the right. So the final momentum of the medicine ball, that's the final momentum, is 25. So we're going to come back up here. We're going to put 25 right here. Awesome. Now we can solve this a couple ways. Let's do the easy way first, right? So we said momentum in equals momentum out. So if the momentum in was 150, the momentum out has to be 150. So let's just put 150 here. And we know that in order for 25 to get to 150, you have to add 125. 125. So that's why this is what it is. Because momentum in has to equal momentum out. Now how do we solve that though? Is we just go back over here. This is the final momentum. Remember? Mass times velocity. So the mass of the skater is 50 kilograms. So let's put this right over here. 50 kilograms times, remember what we said our velocity was? It was 2.5, right? So times 2.5. So 50 times 2.5, well that's 125, right? Because 50 times 2 is 100, and then half of that, half of 50 is 25. So the final velocity equals 125 of our skater, right? So that's how we got this. So that's easy, right? Now the momentum change. So don't mess this up, because you can easily mess this up when you start thinking of like just an easy, you got to think of direction when you think of momentum change. One direction is positive, one direction is negative. Okay? So with that being said, you find it out by doing momentum after. Can we see this? Yeah, there we go. After minus before. That's how we find the momentum change. So momentum after minus momentum before. So with that being said, momentum after the ball's momentum 25 minus after minus before 150 equals negative 125. Make sense? Because you got to think about it. The ball got thrown, and when it hit something, it slowed down a lot, right? It didn't stop all the way because it still has a little bit of momentum, but it slowed down quite a bit. So that means the change is negative 125, right? Now the skater was at rest. So the skater's momentum after was 125. Before was at rest, so that's 0. So the skater's final momentum is positive 125. Which makes sense because there should be no overall momentum change. 125. Which means the total change in momentum was 0 of the system, right? Momentum in equals momentum out. So remember our formula should be equal. So started with 150, ended with 150. There was no like loss or gain. It was just, it is what it is. It was a transfer of momentum, but overall the system maintained its integrity. So there you go. That's how to do it. We solved all these. We solved our final velocity, and we highlighted because highlighting is for geniuses. Awesome job.